Good morning, everyone. So welcome to today's class on K-means clustering. So today we will finish the remaining just a few pages of the K-means clustering. Then we will start with the new topic on the artificial neurons. So recall that in last class we analyzed some of the weaknesses of the K-means clustering. So that is first is sensitive to outliers, and we also try to propose some solutions to deal with the outliers here. And we also said that it's very sensitive to the initial seeds. Actually, the scikit-learn module already provides the solutions to try to solve this problem. That is just random pick some different sets of initial seeds and then run multiple K-means clustering, select the best one. The last weakness is not suitable for discovering the clusters that are not hyper-ellipsoids. And today we will just try to finish, try to compare the pros and cons of the K-means clustering. Pros, it's very easy to understand and implement. If you have already started lab 4, hopefully you will agree with that. It's very easy to implement. And it's efficient given that big K and the number of iterations is small, then it's efficient. Basically, actually, the computations lie in the pairwise distances computation, right? We need to compute the distances between each training data and each centroid. And in total, we have K centroids. So if this K is small, then actually it's efficient. And also, we should also try to restrict the number of iterations because it's some iterative algorithm. So note that usually the K-means clustering is more efficient than KNN. Because in KNN, the pairwise distances is for training data and testing data. And of course, the testing data, we know that is in some comparable scale with the training data. But for K-means, the pairwise distance is between training data and K centroids. This K is usually smaller than the number of testing data. So K-means clustering is relatively more efficient than KNN. Here the cons is only applicable if the mean is defined. Of course, it's K-means, right? So basically means that we have to compute the means. We use the means as the center. So only if the means is defined that we can try to use this one. And we already mentioned in some spaces, the mean is not well defined, like in the hyperbolic space. It's unlike Euclidean distance, unlike the Euclidean space. In hyperbolic space, the mean is very yearly defined, and if we want to get some center, it's very complicated to compute that. Another case, the mean is not defined, is for categorical data. For categorical data, again, is that the features taking some categorical values. If you still remember, what we have used the categorical features, that's again for the animal classification. We can always try to look back at this. It's not classification now, it's clustering, okay. So now we are doing some animal clustering. Basically, we just have lots of animals. We don't know their labels. We don't know which is dog, which is cat, because they are unsupervised learning, right? For the animal clustering, we just want to find the similar animals to group them in the same cluster. And again, suppose we have some categorical feature, color. Black, white, yellow. Just suppose this feature color can take these 3 categorical values. In this case, the means is not defined, right? If we want to do the clustering, first we need to encode all of the string values into some integer values. So for example, we will use 0 represent black, 1 represent white, 2 represent yellow. But in this case, it doesn't make any sense if you compute the average or if you compute the mean of this categorical value 0, 1, 2, right? you possibly get some like decimal numbers, which is not black or white or yellow. For example, you possibly get the average value is like 1.5, something like this. But of course, 1.5 doesn't correspond to any of these color values. In this case, it doesn't make any sense if you just use the mean to represent the centroid, because all these feature values, actually, they're just some categorical values. In this case, we use K-mode. K-mode is a variation of the K-means. So here, K-mode is that the centroid now is represented by most frequent values. So that means in one cluster, possibly in one cluster, you find that, okay, there are some like 10 black and 8 white and 12 yellow. And then you find that in this cluster, among this cluster data points, the yellow has the most frequent values. Then in that cluster, the feature of color should be represented by yellow. So it's kind of like the majority vote, right? So this, we call it K-mode. K-mode is specifically tackling on the categorical features. And know that actually we can try to combine K-mode with K-means together. So that means usually when given a data set, the features, some features are continuous, some features are categorical. Then for categorical features, we use K-mode, and for continuous features, we use K-means. So it's like more frequently, it's a combination of K-mode and K-means. So this is how we can try to slightly modify K-means to K-mode so that we deal with the categorical features. And another concept, the user needs to specify K. Yes, it's not learned by the models. We have to like decide what is the value of K, but still we have some method like the elbow method, hot method to decide the optimal K, sensitive to outliers, which we already illustrated before. So in summary, of course, K-means has like several remarkable weaknesses, but still, if we are talking about the clustering algorithm, K-means is still the most popular because it's very simple, very efficient. And of course, there are other clustering algorithms which possibly use like more advanced techniques, but the other clustering algorithms, they have their own list of weaknesses. Most importantly, actually, there is no clear evidence that any other clustering algorithm performs better in general. In general means that like we cannot find any like proof that actually other clustering algorithm performs better. And in some empirical experiments, we cannot show that. So although other clustering algorithms can be more suitable for some specific types of data or applications, but still in general, they cannot like be better than K-means clustering. So that's why usually we just prefer to use K-means clustering. If we want to deal with like the clustering problem, it's very simple and it's already very good. I know that comparing the different clustering algorithms is a difficult task because no one knows the correct clusters, right? So we don't have the labels. So basically, when we're dealing with clustering, is that we can never compare our predictions with the ground truth labels. So actually, it's very hard to compare them. We can only try to roughly measure the clustering quality. Like previously, we mentioned the inter-class distance, intra-class distance. So we just roughly measure the clustering quality. But still measuring the clustering quality is not equivalent with model evaluation. Model evaluation refers more to the error measurement that we have to know the labels. These are some summary about the K-means. And last would be some remarks about dimension reduction using PCA. Because actually in lab 4, we asked you to do PCA. Even though you only need to like import the module from scikit-learn to do the PCA, we don't require to know the mathematical details. So PCA recall that actually in KNN, we also mentioned a little bit about the PCA, right? We said that usually compute the pairwise distances is quite time-consuming and memory-consuming. In order to save some time and especially save the memory, we can first do the dimension reduction And after that, we compute the pairwise distances. So that saves a lot of memory. Actually, PCA is one of the most popular techniques to do dimension reduction. So it's very easy and very intuitive, most frequently used. Basically, PCA is you try to project the data. Originally, you have a very high dimensional data possibly, and you can try to project the high dimensional data onto some orthogonal feature subspace so that the subspace has lower dimensional. This is used for dimension reduction. Here, the main idea is to reduce the dimensionality of data sets consisting of many variables correlated with each other. That means even though it has many features, but actually some features, they just correlate with each other, so that actually you don't need so many features. Like if you consider customers' features, possibly the weight and height, these two features correlate with each other. So actually, you just only need one feature. So retaining the variation present in the data set up to the maximum extent is a goal of the PCA. So that means it tries to combine correlated data, correlated feature together, but still it tries to maintain some variations in the data set. And it's a common practice to apply PCA before K-means clustering so that you don't need to deal with such high dimensional data, especially later on when you compute the Euclidean distances. And it is also believed that improve the clustering results in practice because PCA, in addition to the dimension reduction, it can also be used to do the noise reduction. So that is possibly when you collect the data, there are some noise in some of the feature values. After PCA, after you find the correlations between the features and try to project it into some subspace, such noise can also get reduced so that it also improve the quality, not only that it be more efficient, also improve the quality. So this is the PCA. If you are interested in the PCA, actually, we also provide a supplementary note for you. So it's, let me see. Not this one. Later on, you will do this one. Yeah, so if you refer to these lectures in K-means clustering, we have this supplementary notes on PCA. So that's, if you are interested, this is for your further reading. You can find all the steps and the mathematical details about the PCA. That's only for further reading. It won't be covered in the exams. Just if you're interested, you can try to do. Yeah, this requires some prerequisite knowledge in the linear algebra. All right, so that's the last remark. Yeah, so any questions so far regarding K-means clustering and the analysis on the K-means clustering?
Would the material in the supplementary notes test in the exam?
No, all the supplementary notes, they won't be covered in the exams. Exams, we only cover the lecture notes and also the lab and PA materials, no supplementary notes. And also the further readings, they won't be covered. So as you can see, actually for each lecture, we provide the further readings, but they are only for further readings. They won't be covered in the exams, so no worry. Just focus on lecture notes and the labs and PA would be fine. Very good. Any other questions regarding the K-means clustering? Great. Then at the end, we also prepared a practice problem for you so that you can try to solve it and compare your answers with the solutions appended here to see whether you already well understand what is K-means clustering. So next, I would like to do a simple quiz in class. No worry, just the quiz won't count to your final grade. Just a quiz to assess whether you already have a good understanding of all the contents we have covered so far. So recall that we have learned 3 machine learning algorithms, right? Naive Bayes model, KNN, and K-means clustering. They are all classical machine learning algorithms, and we call them shallow machine learning because actually they don't involve the artificial neural networks. Later on, we will start the topic on artificial neural networks, but still before that, I would like to assess and also to have just evaluation, so whether you already captured the important concepts in this classical machine learning model. Yeah, so prepared just some simple quiz questions for you. So you can join this quiz by scanning this QR code. It's also a good self-assessment for you, especially before the midterm, to try to see like whether you already like well understand all of these concepts. And no worry, it can be anonymous, so you can just like type some of your nickname to join this quiz, and we won't count it like in the final grade. Okay, so has everyone joined yet? Great, then let's start with the quiz questions. The first would be on the naive Bayes classifier. Okay, I think you need to type some of your nickname so that you can join this quiz. Okay, then let's start our question 1. Okay, the correct answer is true. So, yeah, basically now if we want to calculate this posterior probability, right? This is like the probability of the belief given to evidences is posterior. And suppose we just have no condition independence information. So basically, it's just like the general Bayes model instead of the naive Bayes, because we don't have naive assumption now. Then we have to know the likelihoods. Likelihoods is P E1 E2. P E1 E2 given B. This is the likelihood. We also need to know the prior likelihood, prior probability, that's PB, and the marginal probability, PE1, E2. So note that knowing the likelihoods, the prior, and the marginal probability are sufficient to calculate the posterior probability. So that's the general Bayes formula, right? So this statement is true. So any question regarding this one? All right, then let's check the, yeah, I think after each question it has a leaderboard. Okay, the Bayes is the number 1 currently. Then the question 2. Okay, most of you can get the correct answer. Naive Bayes model is naive because of the assumption is naive. So basically, because like we add a very naive assumption that we just simply assume that all the features, they are conditionally independent with each other. That's why we can get the naive Bayes model. So yeah, it's naive about the assumptions. Okay, the basis is still the number one. Very good name. Then question 3. Okay, this, yeah, a little bit tricky. This is true. Naive-Bayes classifier does not involve optimization of a cost or loss function. If we examine the naive-Bayes model, the whole model, actually we are not trying to optimize anything. We are not trying to minimize anything, right? We only based on the conditional independence assumption and try to apply the Bayes formula. So basically that we try to learn some parameters according to our assumptions, according to we believe there is some probability distribution. Actually no cost function, no loss function is used in naive-Bayes classifier. So this statement is true. Actually, if you look at the 3 models we have learned so far, a naive-Bayes classifier does not optimize the cost function. KNN also does not optimize any loss function. Only K-means clustering tries to optimize the loss function. K-means clustering, if you still remember, we have an SSE. That SSE is the loss function, or we say the arrow function for K-means clustering. So only K-means clustering is trying to minimizing such arrow function or loss function. Naive-Bayes, no such thing. So this statement is true. So remember that it does not involve the optimization. Yeah, this is tricky one. Okay, but the basis is still number 1. Yeah, very good. Then next will be some questions about the KNN model. Wow, half. This is false. Okay, training. KNN has no computation in training, right? KNN is a lazy learning model. Basically, during training process, nothing has been done. No computation has been done. All of the computation happens when we try to test for some testing data, or that means when we try to apply the KNN model to some testing data. All the computations, like the pairwise distances and sorting and the majority vote, all of these steps are doing when we apply KNN model. So this is false. Training KNN classifier takes almost no time, and all of the time in computation actually happens in applying it. So this is false. Yeah, so better to have a review on the KNN. Recall that it's just some lazy learning. Oh, okay. Now number 1 becomes peelings. Where does the basis go? Okay, basis only answer questions for naive Bayes classifier. Okay, I see. Makes sense. Okay. All right, then next one. Yeah. Okay, this is false. KN can be used for regression. KN can be used both for classification and for regression. But when KN is used for regression, we don't do the majority vote. We do the computing the mean for the K nearest neighbors and then get the value. So it can be used for regression. If you already forgot this, no worry. Still, you have time to review the KN lecture notes to see how KN can be used for regression. Okay. Yeah. Number 1 is peelings. Basis is here. Okay. Yeah. Okay, this is true. Actually, there is some fundamental belief that if the training data are more and testing data are less, then usually we see that the error will be lower on average. Note that we only see on average, not that absolutely be lower, just on average. So in default cross-validation, if there is a higher number of faults, that is if D is large, then note that we will only see one fault to be the testing data or the validation data. And then all the remaining D minus 1 faults will be the training data. So that means if D is larger, then the training data will be more. And the validation data will be small, will be relatively smaller. And in this case, the estimated error will just be lower on average. So just considering average cases, it would work like this. So that's why this statement is true. So basically, we need to consider which cases we will have more training data, we will have less testing data. Right? So yeah, another tricky one. This. Okay, the peelings is still the number 1. Very good. Then the last few questions will be about the K-means clustering. Wow, half. This is true. K-means classing algorithm is guaranteed to converge. It tries to optimize the SSE, right? Minimize the SSE. And SSE, if we use SSE as the error function to try to minimize that, and actually it's guaranteed to converge, but it's not guaranteed to converge to global optimal. But it will like eventually converge possibly to some local minima. Converging to local minima is also converge. We say converge basically that it reaches some point that it can never improve in a small neighborhood. So that's converge. And converge to local minima is converge. So K-means clustering is guaranteed to converge. But if we change this statement to like K-means clustering is guaranteed to converge to global optima, then it's false. Okay, so yeah, pay attention to that. It's guaranteed to converge. Okay, this is tricky one. Okay, now the PR is like taking the number one positions. Then the next question. Okay, this is true. Actually, just now we mentioned that one drawback or one cons for the K-means classing algorithm is that we have to specify what is this big K value, right? So this is like we have to specify like how many clusters the algorithm should find. The K is decided by us. So this is one drawback. So this is true. Okay, wow, the number one changed to bar. Okay, then next one. Wow, this is false. Recall that when we first introduced K-means, we said K-means try to find the natural grouping. The natural grouping includes two aspects. The first is that the items in each group, they should be as similar as possible. So that means they should be close with each other. Actually, there is another aspect that is the items in different groups, they should be as dissimilar as possible. That means they should be far away with each other. Basically, there's two standards in the quality, right? The inter-cluster distance and intra-cluster distance. So the aim of K-means is not only to make like the items in the group as similar as possible, also includes like the items in different groups, they should be as dissimilar as possible. So that's why this is false. Well, seems this one is, yeah, totally changed the ranking. Okay, yeah, now our SYL is the number one. Then next. Okay, this is false. The result of k-means clustering actually, of course, it depends on the initial centroids. If you choose different set of initial centroids, the clustering results will also change accordingly. So this is false. Okay, the leaderboard. Okay, SYL is still number 1. And yeah, last question today. Wow, yeah, another tricky one. This is true. Possible. Actually, after some new cluster centers are computed by the k-means, it's possible that a cluster just empty. So the cluster has centroid, but it does not have any data points clustered to this centroid. I know that if I just see that, you don't believe in me, so I actually prepared an example for you. Not me prepared. Somebody else prepared, so I just find that a very good example to illustrate k-means empty cluster example. So if we look at that, so this is our data. We initially have like this 7 data points. We want to do the clustering, and we set k to be 3. So the number of clusters, we just simply set it to be 3. And currently, the shapes like the square and the circle, they have no meanings for now. Because currently, like, they haven't been clustered, so we only have these 7 data points. Here, we use this different shape just to show that naturally we should cluster them into 2 clusters. But somehow, we selected a bad k. We let k to be 3. So, because of course at the beginning we don't know the natural number of clusters in general, right? So we just simply let k to be 3. All right, then we use k to 3 to try to cluster these 7 data points, and then we need to select some initial centroids. Suppose we select initial centroids as like data 3, 5, 6. This is our centroid, initial centroid, and another initial centroid is here, data point 5, another is 6. After selecting 3 initial centroids, and of course we need to try to cluster all the remaining data points into the 3 clusters. Okay, so basically this will be the results. So these 4 data points, 3, 2, 1, 7, will be clustered to the first cluster because initially data point 3 is centroid, and then the data point 4 and 5 will be clustered into the second cluster because initially 5 is a centroid and 6 itself is the third cluster itself is a centroid. All right, after that we need to recompute, right? Recompute all the centroids. So after that we find that, okay, these 3 are the new centroids. Like this is the centroid for cluster 1, centroid for cluster 2, centroid for cluster 3. And we go into the next iteration. Next iteration, we recompute all the distances again and do the clustering. We find that it will be something like this. So after that, this data point 4 will also be clustered into the first cluster. And this data point 5 will be clustered into the third cluster. Then we find that, okay, now the second cluster has no data point assigned to it. Simply the cluster 2 becomes an empty cluster. Of course, the previous iteration centroid remains here, but no data point is clustered to it because if you look at this one, actually data point 4 is closer to the first centroid. Data point 5 is closer to the third centroid. So no data point will be assigned to this second cluster. So eventually we get some empty cluster. And the reason, of course, is because naturally we have 2 clusters, but somehow we let K to be 3. So it's very possible that if you select K to be a very large number, then eventually you just get some empty clusters. Because after a few iterations, the data points will go to their closest centroids. This is an example to illustrate like when will this empty cluster happens in K-means clustering. So any question regarding this example? Yes, please.
How do we handle this?
We just let it remain there. So we just let it remain there. So our clustering results will simply be that we have 3 clusters because we already set K to be 3. And then the first cluster consists of these data points 1, 2, 3, 4, 7. And the second cluster is an empty cluster. The third cluster consists of data points 5 and 6. We will just present the results like this. Even cluster 2 is an empty cluster, we let it be there. And also we need to keep that centroid. This is mainly for testing. Because for the training data, actually we only have like these 2 clusters and 1 empty cluster. But possibly later on, if we have some testing data, that's new data, possibly some testing data can be assigned to the cluster 2. Like for example, if we get some new testing data which lies here, and then it's closest to the second centroid, then we should cluster it to the cluster 2. So yeah, just let all the results remain here. And all the centroids, we should record the centroid. Even for empty clusters, we should record what is the centroid. Very good question. Any other question regarding this example? Great, then let's check our final leaderboard. Wow. Wow, it's a new number 1. Directly becomes a champion today. Very good. Rafe, who is Rafe here? Oh, not here? Okay, didn't come? Okay. Okay, then, yeah, very good. Who is absent but becomes today's champion? Very good. All right, so that's for all the quiz questions for the 3 models. Any remaining questions for all these quiz questions just now? Yeah, just some quick questions to assess your understandings. And in our midterm exams, we will also have 10 true or false questions. So this is just be regarded as a practice for you. So in midterm and in final exams, we will all include such like true or false questions. All right, if no questions, then let's take a 5 minutes break. After the 5 minutes break, we will start our new lecture topic, the artificial neural network. can draw this graph because I'm not very familiar with this graph.
Something like this, and your starting point is like this. So pretty much this, and I sort of like, I don't know how to, but this one is colored in red. So it's different color, so three classes, classes.
But KNN is using the number of in classes.
That's why I actually stand for it.
Oh, okay. K still stands for the 10 years data. So when we try to do classification, we always like refer only the 10 years data. So in this case, and I think it only try to visualize the classification results. So after apply, what is the classification results for this data?
But why is there like some gap between sometimes when we pay with our vision, right? But when you
Yeah, some
gap between.
Oh, this one.
Oh yeah, that one.
Oh, I see. Because when basically it tries to like visualize the results, but still you can try to like from the visualization to see that if you select different K, then the classification results will be different. Please try to visualize this.
Like I mean, it's like for some number of K, there's some area that like it can belong to.
Yes. So that means for this one, possibly sometimes there
So
are
I
some
mean, if the data point exists between, exists in this region, like the train data exists between the region and the
yeah, then it possibly means sometimes. So that because like possibly it will means like among the 3 years neighbor,
But what
then
training
it's,
data are we using for this one? It's like one single point or a lot of points for the training data?
you mean the
Okay, and then because from the example it shows a one train example like one train data point where we will minus the data point of the six. Like samples. Because we have the latest the X right here, and we also have Y is only a single point and like a single point. So like in the lecture example, it does something like
in lecture notes we will only show the classification for one data point like with the key thing. This one is that you can consider actually each of the data points. They will be classified according to the.
That's why the person actually like using other forms because the use of that new data is increased like 300 divided.
You can just imagine each of the data points here actually is classified according to the KNN question index. So each of the data point actually we need to find its K years and then assign it to the majority vote.
majority vote.
Like these points are the training data, and like the other area, like the red region, you just find the nearest free K, which is like maybe like so it will be red.
Okay. So you mean the red region is actually the training data?
No, the red region is the test.
The testing data?
Yeah, so if a test data lies here, then it will be classified into red.
Oh, okay. Now I understand correctly.
Yeah, so if you set K to be different number, then basically the classification result will be different.
I see. So the red dots are, the dots actually are just
Those
the
are training data.
So the white or the
Yeah, and then
the region is
the region is
where
tested.
X is. Oh, okay. That makes a lot of sense.
Now you know more than me.
Okay.
That's what I was
Oh, yeah. Then we just let it. Yeah, if it's empty, then we can select the central one. But still for other, like, that means this empty cluster center won't get updated unless we also assign some new labels. If we like follow the techniques algorithm steps, basically whenever like actually it doesn't change too much. So you have an empty cluster, still you do all the computation like this, but still for this new for this empty cluster because no data is assigned to it, so basically you don't need to update any of the data. Yeah, you can run the empty, yeah, unless they all you assign some new data because it's not converted yet, so possibly they all you will assign new data.
In Excel, we're gonna get some like proving questions. In Excel, we're gonna get proving questions like something like the one that TA showed us yesterday. It was something like proving that. Yeah, it will only converge. Do we have to prove?
No, you don't need to prove. You will only need to remember that it will converge.
Converge.
Yes, you don't need to know how to prove that. All right, after this short break, let's continue a new topic, artificial neural network. Artificial neural network will be a very different topic with all the previous models we have learned, because now it's not every step is so clear. It's not that every step in the model you will be so like sure, so clear about what is going on. Basically, the artificial neural network will be like you try to build the neurons, build the layers together. Of course, you know some general rules, but possibly it's very hard to implement step by step. But for the neurons, still we have some ways to implement it from scratch. So we will start with the neurons, which is the basic unit in artificial neural network. Before that, let's recap what is classification. Classification is the process of predicting the class of given data, right? So it's supervised learning. Like naive-based model, KNN can also be used to do classification. And here the classes, we also call them as labels or categories. Classification examples, we have already talked about spam detection, like try to classify all the emails into two classes, spam and non-spam, and handwritten digit recognition. In this case, we want to classify any handwritten digit here into a digit. So here we have 10 classes from 0 to 9. These are some classification examples. Image classifications, like possibly for any image, we can try to classify it into 3 classes, cat, dog, none of them. That's the animal classification we have used to illustrate always. And why should we do such image classification? Know that image recognition and classification is a subdomain of computer vision. It's an algorithm that looks at an image and assigns it a label from a collection of the predefined labels or categories. And this image classification and recognition, there are some vital components in robotics, such as the autonomous vehicles or domestic robots. So as long as your robots need to identify some visual information, of course the self-driving car has to do this, and possibly the domestic robots have to do this, then the image classification will be applied, will be implemented in such robotics. It's also very important in the security systems such as the face recognition, image search engines such as Google or Bing image search, and medical imaging such as cancer detection. They all apply such image classification. Then specifically for the handwritten digits recognition, it's an image classification, right? Our ultimate goal here is to build an artificial neural network to do such tasks, to try to recognize or classify all the handwritten digits. Know that the handwritten digits input is an image like this. Digital image means that it consists of many pixels. So here, like all of these images, they will be 28 by 28, consists of 784 pixels. Each pixel, I think you already deal with the image data in lab 1. Each of the pixels consists of an integer number from 0 to 255. So if we look into this digital image, it's something like this. All of the 784 pixels, there are some values assigned to represent the intensity value of such pixel. So we can see that's like this. Then our ultimate goal is that we build the neural network so that whenever it receives a digital image like this, it should output the class from 0 to 9. For example, for this input image, we expect that our neural network will output 8. So classify this image into the class 8. So this is our ultimate goal. But until now, we somehow have a little bit difference with this ultimate goal. We have to start with the very beginning with the artificial neuron. What is artificial neural network? It's one of the most powerful artificial intelligence and machine learning algorithm, the most advanced now. Here, an ANN is considered some universal function approximation that transforms inputs into outputs. As the name suggests, it draws some inspiration from the neurons in our brain and the way they are connected. So this is a typical structure of the artificial neural network. In artificial neural network, we have the input layer. Input layer are used to accept all these inputs. For example, possibly we have m-dimensional input from x1 to xm. So each input layer's node will accept one scalar number as the input. And then in the middle, we possibly have lots of hidden layers, and they all like connected together. After like the hidden layers, last we should have the output layer. Output layer will output the thing we want, we expect. For example, we may have some n-dimensional output from y1 to yn. And in the artificial neural network training process, we have two steps. Forward propagation. Forward propagation is simply from input to output, follow this direction. Another process is called arrow back propagation. Then we have to do the reverse calculation from the output layer all the way reverse to the input layer. Yeah, these mechanisms later on we will learn all of them. But now let's see what is the most basic unit, neuron. So we can try to compare the biological neuron with artificial neuron. This is a typical biological neuron in our brains, and this is an artificial neuron which will be used in an artificial neural network. So we know that in biological neuron there are some unit called the dendrites. Dendrites is here. Like if you look at this dendrites, but I'm not a biology expert, so I can only have some rough description about this. This is dendrites. Dendrites basically is used to capture the information, right? So this is a cell, and the cell will capture some other like impulse through these dendrites. So all the impulses carried towards cell body will be passed through these dendrites. And then these dendrites will correspond to the inputs in artificial neurons. Inputs are here from x1 to this xn. They are called inputs. They are just like the dendrites in biological neuron. In biological neuron, we have the cell nucleus here, this one. The cell nucleus, we call it as a computation unit in the cell, in the neuron cell. And then the artificial neuron, we call it node. So this is the node. As you can see, the node consists of the sum and activation function f. So later on, I will all explain like what are the sum, what are the activation function. Then in the biological neuron, we have the axon. Axon is this one. Axon is that possibly after received impulse and after done some computation in the cell nucleus, there will be another impulse carried away from the cell body. This action in artificial neuron, we call it output. So after we get some computation results in this node, then we can have some outputs. So that the output will be outputted by this neuron and possibly will be passed to another neuron later on. So this is the axon and output. And then in the biological neuron, we also have this synapse. The synapse, not visualized here, but synapse in artificial neuron, we call them weight. What is weight? If we look at all the edges connecting the input node to the neuron node, we find that each edge is associated with a number. Each edge is associated with a weight. We call this number weight. Weight is parameters for the neuron. And that means these are the values should be learned by the neuron itself. So these are weights. Like we have n edges here, then we should have n weights. Then the neural node is just simply a linear function, which is sum together with an activation function. So then what is the artificial neuron? So by definition, an artificial neuron is a simple biological neural model in an artificial neural network. It performs certain calculation to detect the input data capabilities. One of the most simplest models of neuron is called perception or threshold logic unit. Basically, perception and threshold logic unit are the same thing, but with different names. Neuron is a more general concept. It's some basic unit in neural network, and perception is one special neuron. It's one of the simplest model of neuron. And actually later on, when we talk about the neuron computations, we will focus on perception because it's the most simple way. For neuron, it's basically consists of the linear function and an activation function. So what is this linear function? Linear function is a linear transformation, which is the weighted sum of input and bias. So actually that's why each of the edge is associated with a weight, because this sum function computes the weighted sum. So that means the first input x1 will be associated with the weight w1, and x2 has the weight w2. It's a weighted sum with all these inputs and a bias term. Bias term is another parameter of the neural node itself. And activation function. Activation function is a mathematical operation deciding whether a perception or a neuron should be activated or not. Activation function basically that after we compute the weighted sum, we need to pass this weighted sum to another function, the activation function, decides whether they should be activated or not. This means that this activation function will decide whether the neuron's input is important or not in the process of the prediction. And note that the primary role of the activation function is to transform the summed weighted input from the node into an output value to be fed into the next hidden layer or as output. So let's see some specific example. Here is an example of neuron. If we look at this structure, input, we only have two-dimensional input. So basically that means each input for this neuron should consist of two features, x1 and x2. And because we only have two inputs here, so we only have two edges connecting with the input and the neuron node. So we have two weights, w1 and w2. The neuron itself should have a bias term, we call it theta. So W1, W2, and theta, these three are the parameters of this neuron. Parameter, that means during the training process, the neuron should learn what are the values for W1, W2, and theta. The neuron itself consists of the weighted sum and an activation function. After that, it gets some output. So this is an example of neuron. So the output should be the activation function f takes W1 times x1 plus W2 times x2 plus theta. This is the weighted sum, right? Weighted sum of the input and the bias term. We put it as the input for the activation F and then get the output. Suppose we have one input, x1 is 3, x2 is 5, and suppose we have the weight and the bias parameters at these values. W1 is 0.2, W2 is 0.3, theta is 0.3, and suppose we have the activation function F takes this one is 1 divided by 1 plus exponential of negative x. Then we have all the required elements to calculate the output. Now the output should be the F with this weighted sum, right? We know all of these values, just simply substitute them, and that's 2.4. And then we pass this 2.4 for this activation function F, we get the result is 0.91683. So this is a typical example of neuron. But still we are unclear about some things. What is this activation function F? Why the activation function F looks in this way? Can we choose some other activation functions for neuron? So first let's try to look at this one. This one is called sigmoid activation function, or another name is logistic activation function. So for this activation function, it takes this form. Fx is 1 over 1 plus exponential of negative x. Now that for this activation function, sigmoid, it takes any real value as input and outputs values in the range of 0 to 1. So if we try to visualize this sigmoid, we find that it looks like this way. The graph, the value range is between 0 to 1. So like no matter which value, as long as it's some real value, you can give it as an input and all the output should be in the range 0 to 1. And the larger the input, then the closer the output value will be 1, right? So it's an increasing function. Increasing function, if you have some larger inputs, then it's closer to 1. If you have some smaller input, then output will be close to 0. So this is some like mathematical analysis we can have from this function. Then what are the properties when we use it as an activation function? Sigmoid is one of the most widely used activation functions. It's commonly used for models where we have to predict the probability as output because of its good property here. The value range is from 0 to 1. And we know all the probabilities, they lie in the range 0 to 1 by definition. So that's why usually we associate the sigmoid with probability. So if we want to predict the probability, then typically we just use sigmoid activation function because it will output the correct value range. And it's differentiable with a smooth gradient, so a very good property. When we try to choose activation function, actually we always care about whether it's differentiable or not. But still the sigmoid has its own limitations. The limitations will be discussed later after we learn the multi-layer perception, because at that time we can see some specific cases that the sigmoid is not so satisfying. So this is one activation function we may choose. And note that for neurons, there are many choices of activation function. So that means for this neuron, actually you can choose this F to be sigmoid. You can also choose this F to be some other activation functions. Depends on which task you want to deal with. Like for sigmoid, basically if you use sigmoid, that means your task is trying to predict the probability. In this case, sigmoid is very proper, very appropriate, good choice. And later on, we will also see some other choices for the activation function. So until now, any question regarding the neuron and the sigmoid activation function? Yes, please.
What is the bias needed for?
The bias, oh, very good. The bias, it tries to shift the weighted sum. So that means if we do not have the bias term, then basically for any input, we directly get the weighted output and pass it to the activation function. But sometimes it's not so good because possibly this input x1 and x2, they are not normalized. And possibly like the weighted sum will be quite away from 0 or from some value we prefer. In this case, we add a bias term, theta here, to try to shift the weighted sum, so that we can shift it to some smaller value or a larger value. Then it will be a good input for the activation function. So it's mainly for shifting the weighted sum.
Are we using the same activation function throughout the whole perceptron layers, like across different perceptron layers?
Good question. Usually in a neural network, for the same layer, we use the same activation function. But for different layers, we actually sometimes we choose different activation functions. But the same layer, just use the same one. Yeah, good one.
I mean, would exit 1 give you an answer? I mean, if the error is like some, I mean, if you add the error and the error is 0.3, then
You mean the bias term?
oh wait, actually, never mind. Yeah, never mind.
Okay, maybe you can ask me later.
Can you
Yeah.
explain again why differentiating it would make it a good
Oh.
activation function?
Differentiable.
Yeah.
Oh, yeah. This is basically for the neural network. For neural network, we need to do backward propagation. When we do the backward propagation, we differentiate the loss function. So we expect that it will be good that all the functions we have used is differentiable. Like weighted sum, of course, is differentiable. So we also want that this activation function is also differentiable, so we can do backward propagation. But this is, if we'll consider a single neuron, then this is not required. But if we consider a neural network that we connect all the neurons together, this is required. Only for the neural network construction, we require differentiable. Yes, good question.
So this to construct the backward.
Yeah, backward propagation.
So it helps in constructing the equation that allows it to go backward.
Yeah, to go backward to update the parameters. Yeah, very good. Yeah. And yeah, very good. Other question regarding the neuron and sigmoid activation function? Great. Then let's see another activation function. So we have seen that activation function has many possible choices. Sigmoid is one of the most widely used one, and here is another one called binary step activation function, which is very simple. Fx can only take two values, 0 and 1. So if the inputs, actually the input for activation function we know is the weighted sum. If x is negative, then fx outputs 0. If x is non-negative, larger than or equal to 0, then fx outputs 1. Note that when using the binary step activation function, a neuron is called perceptron. So perceptron, this name specifically refers to that a neuron uses binary step activation function. If it uses other activation function, for example, if it uses a sigmoid activation function, then we still call it neuron. But if we use the binary step, we call it perceptron. Binary step function just looks like this. Very simple. Can only take 0 and 1, these two values. In this case, note that the binary step active function cannot provide multi-value outputs. Right? It can only output 0 and 1, unlike sigmoid. Sigmoid can output any value between 0 and 1, but binary step only 0 and 1. Thus, usually the binary step activation function cannot be used for the multi-class problems. And note that the gradient of the step function is 0. So if you try to get the derivative of the binary step function, the gradient is 0 for this part, 0 for this part. Basically, it's 0. Of course, the gradient is not defined at this point, 0 point. But anyway, in both sides, 0, which causes a hindrance in the back propagation process in multi-layer perception neural network, so which will be covered later. Later on, when we talk about multi-layer perception, we will see, tell you like what is the back propagation and why the gradient the differentiation is so important in the activation function. But even though it cannot be used for multi-class problems, it cannot be used for MLP, still binary step activation function is very suitable in one task. It's very suitable to represent some logic operations in a neuron. Because the logic operations will only have 0 and 1 as output, right? Logic operation, basically, it only has two values, true or false. We use 1 and 0 to represent. And we can see an example here. We want to use a perceptron to learn the logic AND logic operation. So we just work on the problem of AND logic operation, and we know the truth table of logic AND is like this. If x1 and x2 are both 0, output should be 0. If any of x1 or x2 is 0, the output is still 0. Only if both x1 and x2 are 1, the output should be 1. This is the truth table. If we want to use a perceptron to learn the AND logic operation, that means we will treat this table as our training data. Our training data has 4 data points. And the data is 2-dimensional data because we only have x1 and x2, right? We have 2-dimensional data, and the last column output is label. So that means actually we are trying to do some binary classification. We have class 0 and class 1. The output is just we treat it as the class label. All right, so we want to use the perceptron to learn such logic AND example. Then that means we want to learn the parameter values W1, W2, and theta, so that eventually this perceptron can correctly predict all the data samples in such truth table. We have to start with initialization. If we don't have any initialization for this W1, W2, and theta, then later on it's problematic to update them, right? We have to update them on some initialization. So assume that the weights and bias are randomly generated initially. So we just get the random initialization like this, and we set learning rate eta to be 0.2, and then we select activation function as a binary step function because binary step function only outputs 0 and 1. So which is very suitable, we can say which is almost perfect to represent the logic operation. But still, questions remains, what is this learning rate? And also, after we initialize all these parameters, how to update them? So we will leave this question to next class. Next class, we will talk about the rules to update all the parameters in a perceptron, and we will also use this as an example to show you how to learn the parameters for a perceptron. So see you in next class.